Okay, so what we're going to do is we're going to move on to test three material now. It'll include three main topics. It's actually two parts. Polarity and molecular interactions, and well, three parts. Polarity and molecular interactions, uh, carboxylic acids, and then lipids. Okay, so we're going to cover polarity now. Hopefully, this is a review from an intro chemistry class, but we're going to apply. We want to apply this principle to the material. We could have applied it to carbohydrates, um, and I'll explain why when I get into molecular interactions. But it applies to lipids, proteins, and nucleic acids. So polarity is a character determined by how the shared electrons between the atoms of a molecule are distributed. So let's take a look at H2, hydrogen. It has has a covalent bond where there's two electrons shared between the two atoms, one from each atom, and so there should be one. It has one covalent bond. One of the things they should have learned in your first chemistry class is the concept of electronegativity. Now, I don't want to go back over all of this, but I'm going to do kind of a review and really just pinpoint what's important to know about it. So, electronegativity is the ability of an atom to attract electrons. And this is a pretty powerful concept in all of chemistry. In intro chemistry, at least from my class, you learned that this ability, electronegativity, is determined how close the protons are to the surface of an atom. The smaller the atom, the closer the proteins are to the surface, and therefore have a higher electronegativity. When you go over this, you will find that there is a trend in the elements in the periodic table. The ones up and to the right, okay, so this is the periodic table. Okay, elements up here will have higher electronegativity, and elements down here will have low electronegativity. And if you notice, the elements that we work with in this class, carbon, hydrogen, oxygen, and nitrogen, are up here in the high electronegativity group. And it's not a coincidence, okay? It has to do with covalent bonds. And we'll leave it at that for now. Okay, so let's go back to H2, each hydrogen. So, because of the concept of electronegativity, both of these atoms are pulling on this shared pair of electrons, okay? And they're actually pulling at the same strength and in equal but opposite directions, okay? So what that means is basically this shared pair is kind of stuck in the middle because neither one of these guys can pull it away. So it almost looks like it hasn't moved at all, and therefore it's equally distributed. That shared pair is equally distributed between the two atoms. Okay. Now let's look at HF, hydrofluoric acid, or hydrogen fluoride. Okay, now fluorine has a higher higher electronegativity than hydrogen. In fact, it has the highest electronegativity of any atom. And so when you connect it with the hydrogen, hydrogen has its pull on the shared pair, but fluorine has a lot stronger pull. Okay, now it's in the directly opposite direction, but it's a lot stronger. So overall, the electrons are going to be pulled, okay, towards the fluorine. So if this was a tug of war, you would notice is that the shared pair would be shifted over closer to the fluorine. Okay, when that happens, fluorine becomes a little bit more negative because the electrons are shifted over, and hydrogen becomes a little bit little less negative because of that pull, and so it becomes a little bit more positive because of the fluorine pulling electrons. So now so the hydrogen doesn't have as much electrons on its side anymore, so it has a little bit plus side, and the fluorine has a little minus side. Now, if you look at this, the way I drew it, okay, it looks like kind of like a bar magnet. Instead of having a south and a north, okay, it has a plus and a minus, okay. And so this molecule is a pole. It has a plus electrical pole and has a negative electrical pole. So it's called electrical pole. So this molecule here is a polar molecule. And that's because it has an unequal distribution of electrons. Okay, so in the first case, the H2, there was no electrical pole because they were equally, the atoms were sharing the shared pair equally. And so this molecule, instead of being polar, is called a nonpolar molecule. All right, so here's the key things here. So when electrons are equally distributed, like in the case of H2, then the molecule is nonpolar. And when electrons are unequally distributed, that means shared, pulled, or pushed, unequally shared, pulled, or pushed, then the molecule is polar. Okay. So let's take a look at an example of BeH2. Okay, and what we're going to do is concentrate on, we'll have beryllium in the middle, and then we'll have the two hydrogens pulling on the beryllium. All right, now this should look a little bit like H2. Okay, is that the hydrogens are pulling in opposite directions at equal strength, and therefore the beryllium basically stays exactly where it is. And kind of like these two dogs here, little twin puppies, okay? They look like Humber Spaniels. So they're both pulling on this dog toy, and it's probably not going anywhere, okay? All right. So this would be a nonpolar molecule, because the beryllium, in a sense, is equally shared between the two hydrogens. Okay, now let's, again, like we did before, let's replace one of the H's with F. Okay, and in the same case before, what's going to happen now is the fluorine is going to have a stronger pull, and what's going to happen is the hydrogen over here is going to become less negative, so it's going to be positive, become more positive, and the fluorine is going to become more negative because it has pulled the electrons towards it. And so there's an unequal distribution of electrons, and the hydrogen's more positive and the fluorine's more negative. And this is a polar molecule. Okay, now let's do water. So water is H2O, and you can draw it like this. And again, it kind of looks like BeH2. It looks like they would cancel each other out. Well, that's not the case at all, right? It's not going to be like the two dogs pulling on this rope here. They are not going to cancel out. Okay, let's look back at the BeH2 and the BeHF, because one thing we're going to see in this case is that it has to do with something else. So the shape of both these molecules from test 1 material, if you go back and look, if you have a molecule that has, so BeH2, okay, it was Be, okay, so this molecule, it's a center atom, had two attachments and no lone pairs, and we said when you have that case, it's a linear molecule. That means all the atoms are in a straight line from each other. Okay. And that helps, so when they both pull, these two hydrogens are pulling on them, they're pulling in the same direction, in the same line, so they cancel each other out. Okay, so let's look at water now. Okay, now water, like the beryllium dihydride and beryllium hydride fluoride, it has two attachments, but it also has the two lone pairs. Now, if you go back and look at test 1, if the molecule has, the center atom, has two attachments, or two connections, and 2 lone pairs we said it was bent. And so we could draw it like this here. So you got to remember when we draw these, we're drawing them 2 dimensions, but really they're 3 dimensions. So this view that I just had on the previous, okay, is like a top view, looking at it from the top. And then if you turn it on its side, it's going to look like this. So now, is there an equal pull on the oxygen from the hydrogens? Yes, there is, but the directionality is an account. So here's a picture. I have this guy here. I found it on the internet, and he's got 2 dogs pulling on him, and this is an unreal case. But let's say there's a dog, 2 dogs pulling on him, and they're all pulling on him in the same line. Okay, so and if this was happening, this guy would stay exactly where he is. Right, but now let's put him on the ground and have him like this. Okay, so what's going to happen is these guys are pulling on him. Okay, they're both pulling on him out, going out this way. They're trying to get out this way, and that's canceling out. But they're also pulling him down. Okay, so what he's going to end up doing is he's going to feel that pulling down, and actually it's going to be quite uncomfortable. He's going to be feeling like he's being pulled down. All right, and he will be pulled down if he doesn't watch it, and so he has to hold them up. So so this is going to be like water. So you have these 2 hydrogens pulling down on the oxygen, and when that happens, the oxygen gets kind of pulled. The electrons of the oxygen get pulled down. All right, and what that does is it causes the molecule to be polar. Okay. So the hydrogens are pulling the electrons down, and so this side down here is more negative. It should be pointed like this, and the other side is going to be more positive. So this water is a polar molecule for a different reason. Okay, we'll talk about that in a minute. Instead of having a different atom attached, it has a different shape. Okay, and that's the key thing here. So what determines polarity, and this is the key thing, this really big thing, okay, is there's 2 things that determine polarity, okay. One is the electronegativity differences of the atoms attached to the center atom, and that's like in the first case of beryllium dihydride, and they won with fluorine. Okay, they had same shape but different atoms attached. And then you have the shape can make a difference. And this is like comparing water and beryllium dihydride, which had the same kind of atoms attached but have different shapes. Okay, so these are 2 things that determine polarity. Okay, it's important for us to know if a molecule is polar or nonpolar. Really important for this class. But I don't want to go through all this, figuring it out, maybe drawing out the structure and finding out electronegativities and fusing the shapes and all that. It gets complicated. I mean, if you're really, really interested in it, you really need to have figured out, you should do it. Okay, but what we're going to do is we're going to use a quick way to figure out the answer. And we're going to use rules of thumb. And what that means is basically some things that just help us figure out the answer fairly quick. All right. So we're going to have two rules of thumb here. These are not reasons, or these do not determine if a molecule is polar or nonpolar. These just tell you how to identify. Okay. So in the last slide, it told you how to determine. These tell you how to identify. So the first rule of thumb of polarity, if you're given the bonding structure, like we've been doing in the last couple slides, if the center atom has all the same things attached to it, it's nonpolar. If it has at least one different type of thing attached to the center atom, then it's polar. So let's see if that works. So let's look at BeH2. We know this is nonpolar, but let's see if my rule of thumb works. So the rule of thumb says if the center atom has the same things attached, same type of thing, then it would be nonpolar. And voila, it is. Okay, so it does. So this does give us, so far, seems to work. Now let's try it with this guy here, which we already determined is polar. Okay, and you notice that it has two different types of things. And so we said if it has two different types of things attached to the center atom, then it's going to be polar, and that's what we determined up before. All right, now let's go to water, and this might be a little tricky. Okay, does does the oxygen have the same type of things attached? Well, kind of looks like it, doesn't it? Well, you got to be careful here because thing, okay, thing not only means atoms, it means lone pairs. So water actually has two different types of things. It has hydrogens and lone pairs, okay, and therefore it is polar based on this rule, and that's what we found out with water anyways. So this rule of thumb does work most of the time. In our case, it will work all the time. All right, the second rule of thumb only deals with certain types of molecules, ones that have carbon, hydrogen, oxygen, and we could even include nitrogen. And these are the types of molecules that we deal with in this course, because all of the biological macromolecules have carbon, hydrogens, and oxygens. So the only thing you need here is the chemical formula. You don't need the bonding. And the rule of thumb goes like this. And it works most of the time, again, it's just a rule of thumb. If the ratio of carbons to hydrogen is greater than 3 to 1, the molecule probably is nonpolar. So let's look at a couple of examples. So that C2H6O. And what is the ratio of carbons to oxygens? Well, there's 2 carbons for every 1 oxygen, 2 and 1, which is less than 3 to 1, so this is a polar molecule. Okay, so let's look at this guy here, C12H26O2. The ratio of carbons to oxygens is 12 to 2, okay, or 6 to 1, which is greater than 3 to 1, so this is a nonpolar molecule. Okay, and that's it for this slide, and I will do molecular interactions next.